John.
All right. Thank you, Maria. Appreciate that kind introduction. And first of all, we all want to welcome you to FRP RCS 16 on behalf of the co-chairs. And we wish that you have an excellent time here in New Orleans. So besides the technical events and sessions, please do get out and visit some of the culture and the history of this wonderful American city. I'm going to have a couple of shameless plugs here because we have a number of international attendees, and just wanted to let you know where we're located. Basically, north, we're located at the universities in central Missouri, right between Springfield and St. Louis on Interstate 44. We were founded in 1870, and we're the oldest STEM campus west of the Mississippi River. And we are essentially north of where we are right here in New Orleans. One of our big additions has been a $7.5 million advanced construction materials lab. This connects to our structural engineering high bay lab. And for all of you interested maybe in doing a sabbatical or something along those lines at some point, you're more than welcome to contact me for that opportunity. 80 to 85% of our students are in engineering, and you can see we have 17 different engineering programs. So that's the most of any university in the United States. And lastly, Maria mentioned our Missouri Center for Transportation Innovation, and I just wanted to mention this because we have a big project. It's going to be about 7 to 10 years, which is the widening of Interstate 70 all the way from St. Louis, Missouri to Kansas City. So that's over, I think, 230 or 40 miles. And that will involve replacement of all the bridges along the interstate from St. Louis to accommodate 6 lanes of traffic. So we're hoping it'll be a test bed for innovation, an opportunity to try out new materials, sensors, and hopefully FRP will have a role in some of this work. So with that, I'm going to then jump into my presentation. And as you can see, the title of this is Review and Analysis of FRP Bond Lengths from Pull-Out Testing Database with Reduced Embedment Lengths. So kind of the background for this work was a little over a year ago, I was on sabbatical at WJE in Austin, Texas. And in some of the projects they deal with, they want to develop continuity between existing concrete, new concrete oftentimes. And that might involve utilizing a non-metallic material like FRP. And so some of the questions came up, well, when you have very short embedment lengths, how well does that work? That was the first part of the question when it's embedded in concrete. And then, of course, there's more of the repair approach where it may be drilled in like a dowel and epoxy anchored in terms of that application. And so one of the things we wanted to look at, or I wanted to look at, was in our ACI 441R, it talks about linearly reducing the bar stress from our bar stress equation from an embedment length of 20 bar diameters or less. And most experimental research and data examines the development length of various FRP bars at longer, more traditional embedment lengths. So I wanted to collect data on that, test data already out there, and sort of analyze that. So this investigation looks at that short embedment length into concrete. And the second part of that question was, what about epoxy embedded dowels into reinforced concrete? And so I'll go through an introduction, background, talk about the research investigation that was undertaken here, and wrap up with some conclusions and some future suggestions. We're all aware corrosion of reinforced concrete is a major factor to deterioration of structures, and $276 billion per year in the U.S., which is 3.1% of the U.S. Domestic product. So to reduce corrosion rate or delay the corrosion is very important from a reinforced concrete structural perspective. And so some of the advantages, we're all pretty much experts on FRP in the room here, but we know a lot of these advantages. I won't read them. But again, looking at how this affects it, some of the limitations, and also some of the C sub E factors involved. Usually there's one of 4 tests that are typically looked at for bond testing. At Missouri S&T, we have done the beam splice test as well as the pull-out test. The beam splice test is more on full-scale or mid-scale beams, so those are, of course, more expensive than a smaller pull-out test. So this particular work is going to focus on collecting information and data that I was able to locate in pull-out testing. We know a lot of factors affect the behavior of reinforcing pull-out in concrete. Obviously, the surface treatment of the bar, whether it's deformed or smooth. Most of our FRP bars, we're counting on friction rather than friction as well as mechanical bearing. There's also the chemical adhesion of the bar, the concrete strength, the reinforcing bar type, the stiffness of the bar, the placement in the concrete cup. So these are all factors that affect bond. And of course, mild steel has that advantage of the bearing due to the lugs. But FRP bars also have some different types of treatments that are done that may enhance, oftentimes, the bond performance. And keep in mind, steel, of course, is homogeneous, all properties any direction. FRP typically will have the fibers running in one uniaxial direction. So in terms of failure modes, when we look at a pull-out test and tension, it could commonly be a splitting failure of the concrete, a concrete pull-out failure where you pull out the cone of the concrete if the bond of the bar is very, very good, or it could be pull-out of the bar itself. And you'll see there on the right-hand lower figure, typically a GFRP bar. That's one of our tests in the lab that was done. You can see the resulting of the pull-out of the bar from the concrete. So oftentimes, it's obviously, especially in very short bonded lengths, very difficult to rupture the bar, right? If we're going to look at how we can analyze or look at the results, of course, this equation gives us the average bond stress. And in our ACI 441R15, we have this equation here that gives us the maximum permissible stress in the bar that can be developed. And again, you can see the point I mentioned earlier that at 20 dB, it mentions to linearly reduce it down to 0 along that line. So just as a case study, I took an example where we have 5,000 psi concrete, a number 5 GFRP bar that has a tensile capacity of 105, stiffness as you can see, and also using an example where this would be doweled into the concrete with an epoxy material of 1150. The figure on the right, you can see the red dashed line, which would be the actual tension failure of the bar, if you were to obtain that. The bottom, you can see varying short embedment lengths. And then you can see 2 lines. The lower line is the bond adhesive failure, if it's not completely bonded in concrete, using the example I gave you. And then the blue line is the concrete breakout failure of the concrete. And then you can see some actual test data with a 3.5-inch embedment length, number 4 bar and number 6 bar, that shows the failure in concrete. This was not adhesively anchored in concrete for the 2 different bar types. So we can try to predict what type of failure mode will occur depending on the parameters that we're looking at. So for this study, these were the papers. I know it's a little bit hard to read in the back, but this is all in the paper, of course. These are the papers that were collected. And these were the ones that I could find with pull-out type testing in the test example I showed you earlier. And you'll see in there's glass bars, there's carbon bars, and there's basalt bars. And you'll see there's also different bonded lengths that were in these particular pull-out tests. Most of them were in conventional concrete, but some tests were actually done in some specialty concretes, and then also there were some that were done under varying temperatures to see the effect of temperature, and there were some that looked at the microstructure of the failure mode and the FRP aftertest. So, how to approach this analysis? Since all of these tests, had a lot of different bar properties, we know that the FRP bar properties vary, we know the concrete varies. I was like, well, how am I going to look at this in terms of the maximum persistible stress in the bar? And so I decided to look at it from a perspective of upper and lower bandwidths based on that database of papers collected, and benchmarking that to the ACI 441R equation 10.1c. So let's first look at how GFRP performs. So out of those papers that I was able to collect, this sort of summarizes the bar area within a grouping that might vary dependent upon the manufacturer of the bar. The middle is the range of concrete strengths in all these papers. And then the right-hand column is the tensing capacity manufactured guaranteed property range of all these papers. And then, of course, we would want to apply the C sub E factor, right? If this is an actual practical case. So when first looking at some of these data, just to kind of give you a feel, if I use a 0.625 inch diameter bar, 105, and I vary the compressive strength, what do we see? We see improvement in the bar stress, of course, as we improve the compressive strength of the concrete, just to kind of give you a feel. If we fix the concrete strength, for example, at 6,000, and we vary the bar diameter, as the bar diameter gets larger, the maximum permissible stress gets lower. And for most manufacturers, as the bar diameter gets larger, oftentimes the tensile capacity of that bar also goes down a little bit, right? So this gives you an idea in terms of how some of these properties will affect it in a small parametric study. Now, when we look at the data that was collected in these pull-out tests, first we'll look at a number 3 bar with GFRP, and those two lines represent the upper and lower bounds of those ranges of concrete strength, tensile capacity, and bar area. So you can see even within these papers and that equation, it doesn't really influence the maximum permissible bond strength that much. And the first takeaway for this limited amount of data that I was able to locate is that we look pretty conservative, right? And also when we move up to the number 4 bar diameter, again, we are quite conservative. Now, if you look at the left-hand figure, you see this point here, 20 bar diameter. You can't really see it up here. So when you get to this point, for example, you see that you've reached that 20 dB in terms of the behavior down to 0. So when we move up to the number 5 bar, again, the results we see are all pretty conservative. And when we move to the number 6 bar, again, conservative results. However, I'll point out that some of the test results that were done in high volume fly ash concrete, you start to see some different performance behaviors. So maybe as we move into some of these specialty concretes, it could be where a calibration factor could possibly be needed. So just for the GFRP, we can see that in general, we see nice conservative results, which is good for the number 3 bar and 4 and 5 bar, and then we start to see some closer in the larger bar diameters, including those with specialty concrete. Now, if we move to BFRP, and the hope is to, of course, implement BFRP in a future version of the 440 documents. Again, here's kind of the distribution of the data collected. All of this is in the paper. And now when we start to look at some of these results, we start to see that some results for the number 3 bar, the number 4 bar, start to show, hey, maybe this isn't always conservative for all of our data set. Okay, so take this at what it's worth. In our poster session this evening, we've done some basalt pull-out tests on one of the posters, and the results that we got at very short embedment lengths seem fine. For the number 5 bar, similar. Number 6 bar, there really wasn't a lot of results that I found, but our results were fine for our particular study. And again, some of these data sets are kind of lacking. But what do we see with the BFRP? We see a little bit less conservative nature. We see some of the data which sort of raises, hey, this may be something to look at implementing for BFRP bars, and perhaps I would say do more testing on this. Maybe more is out there, I know. Now CFRP, are we going to put CFRP in a very short embedment? Probably not, right? High strength, high stiffness material. And there was very limited data that I could pull that I found in the pull-out test. Here you can see this is kind of a blow-up of number 2 bars. Very, very unconservative. Number 3 bars, unconservative. And number 4 bars, unconservative. And if I read 440-15 correctly, it does not distinguish between bar type. That equation basically applies to everything. So I don't know how closely we've looked at this for some of these other bars. So again, very limited database. So I don't want to draw too many conclusions on the CFRP. Just a heads up for us to kind of keep an eye on that. So some of the overall concluding remarks and takeaway, I'd say a larger portion develop a much higher bar stress. I did apply the factor for glass. It was 0.7, obviously. For CFRP, it was different for the C sub E factor. So they appear conservative for GFRP. If there's any adjustments, maybe there could be some calibration factors for different types of concretes, or to make it a little bit more economic for some of these short cases. And in the case of the BFRP, about 15% of the database appeared to be unconservative, from what we saw in those figures. And then for CFRP, very limited, probably usage in that type of application, but that did kind of raise the flag on things there. Future work, continue, I think, to develop more databases on this. Look at any gaps in, for example, surface treatments, those sorts of things. Further look at bond performance and reduced embedment lengths. I know we have some presentations on shear friction at this conference. That's a needed area where we have these bars in the shear friction application. And then try to look at maybe some of these surface treatments a little bit closer. And I would say, I know that some of the adhesive manufacturers, I don't want to name any names. They've done some testing already with their products for adhesively anchored. But to me, that's an area in our standard which is a gap that we need to look at. If people do want to drill dowel and epoxy FRP bars into concrete. So that's an area, I think, for research. And I want to just end with thanking one of my students. Sadiq helped me collect the data, so I want to thank him. And I also want to thank some folks at WJE when I was there on my sabbatical. Chuck LaRoche, good friend Jeff West, Lee Lawrence, Steve Foster, Matt Carlton, and Brian Merrill. They were great to work with. And sort of the inspiration to look at this came from my time at WJE. So thank you very much for your attention.